Welcome to the lectures of Power System Dynamics and Control course. So last class we discussed about the stability analysis using classical models power system. So already we discussed how by considering the most simplest model, that is classical model, we can analyze the power system stability, both the small signal stability and also the transient stability. Both we can do. So already we did the analysis, and one assignment I have given, it is pending today. So please submit today. Everybody request all of you to submit today. So today we'll see the modeling of synchronous generator, because we have seen there are various components in a power system. So before we go with a exact model of the power system for dynamic analysis, we must model mathematically all the components of the power system. And the most important component is the generator, because in the generator we have various elements, and it is dynamically also very important to know the dynamic aspects of various components in a generator. The generators generally we have, if we'll consider the synchronous generator, we have rotor and stator part. These are the important parts, of course, rotor and stator. On the rotor we have field, exciter, and on the stator we have the armature winding. And except this rotor and stator part, we have also other components, like we have exciter is on, of course, in this rotor part, right? And of course rotor is consisting of the field winding, and field winding is excited by some exciter. There are certain mechanisms, there's many exciters are available, and also apart from this we have governors, which governs the steam input to the turbine, and also apart from this turbine system is there, right? Okay, we'll see one by one the modeling of the generator, and each component will model and we'll see it. So this is a typical generator we can see here, where in fact the generator is connected to the network, right? Here we can see this is your network, and it is connected through the circuit breaker, then step-up transformer, and the synchronous generator is connected through the step-up transformer to the network. And of course, in the synchronous generator, we have various elements we can see here. This is your generator, right? And we have also exciter, right? And turbine, then the governor system, right? So here we can see that in order to control this synchronous generator, we need all these components: exciter, governor, and turbine, right? So these three elements, they play a very important role to dynamically control the output of the synchronous generator. Therefore, we have a measuring element here by which we measure the terminal outputs, and it will be fed back to different components. Like we are seeing here that VG and IG, the voltage and current at the terminal, they are measured and they're fed back to the automatic voltage regulator. Of course, we have a V reference here, right? And through this automatic voltage regulator, AVR will give feedback signal to the exciter, and accordingly the exciter will feed to the field of the synchronous generator, right? And similarly here we have power and frequency. It is measured at the terminal of the generator, and it is fed back to the governor system, where it compares with the P reference, and then the governor actually helps to adjust the valve here, which actually helps to control the working fluid inside the turbine. Working fluid may be water, may be steam. It is based on the different types of the type of the generator. If it is a steam turbine, then it, of course, the working fluid is steam. And if it is a hydro turbine, of course, the working fluid is water. Similarly, of course, in the gas turbine, the gas is the working fluid. Okay. So now this is the whole unit of the generator, we can say, right? And it is working in coordination with all its elements, exciter, turbine, governor, and of course, the measuring elements plays very important role to give the feedback signal. And another important unit we have is here auxiliary transformer. This auxiliary transformer, or sometimes we call it unit transformer of the generator, which in fact feeds the power to the auxiliary services of the generator. Sometimes it feeds the power to the exciter, sometimes other auxiliary equipments, like there are various pumps, various motors are connected, and it helps in the boiler, in the turbine, right? So there are many feed pumps are there. So they need the auxiliary supply, and the auxiliary supply, in fact, it is connected through an unit transformer. Okay, and sometimes it is assumed that 10% of the generated power is consumed by its auxiliary itself. Okay, if it is a 200 megawatt generator, then around 20 megawatt is actually used for auxiliary supply. Okay, there are various auxiliary requirements. Okay, so now we can see various exciter arrangements in a generator, right? So here we can see here, this is a kind of generator, exciter arrangement. This is your synchronous generator where on the starter we have the armature winding and it gives the output, right? And we have on the rotor, we have field winding. This field winding is on the rotor, okay? Rotor of the synchronous generator. And this is connected through main exciter, which actually supplies the DC supply to the field winding, right? So this this main exciter plays very important role. In fact, this main exciter is also driven by auxiliary exciter. The auxiliary exciter supplies to the field of the main exciter, right? And then the exciter of the auxiliary exciter is supplied via AVR, automatic voltage regulator. And this main exciter, in fact, if we see, it is a DC generator. So if it is a DC generator, if it is, suppose it is a separately excited DC generator, then of course in the DC generator, the armature is on the rotor. Okay, it is connected through the commutator segment and commutator and slip ring, and through the commutator we get the supply at the terminal, right? And then this DC supply will be connected because here the field is rotating, it is on the rotor, right? So therefore we need to feed this DC supply through the slip ring. This is your slip ring, huh? SR. These two are your slip rings, okay? So through the slip ring we feed the DC supply to the field of the generator, okay? So this is one arrangement. And another arrangement we see here, this is the main exciter here is a AC generator, and the AVR is being fed. And this AC generator, we have three-phase supply, and through the rectifier, we are rectifying it, and through the slip ring, we are feeding it to the field of the synchronous generator. This is another arrangement, right? And one more arrangement here is similar kind of arrangement, but here we have the main exciter is the synchronous generator itself, okay, and here sorry, the field is on the starter. Here it is AC generator where the field is on the starter, which is being fed by the AVR, and the the armature is on the rotor. Okay, this armature in the AC generator is on the rotor, and therefore we are putting here one rotating rectifier in order to feed to the field of the synchronous generator. The field of the synchronous generator is itself on the rotor, same rotor. So both are on the same rotor, right? So here the armature winding of this exciter, main exciter is on the rotor, and here the field of the synchronous generator is on the rotor. So therefore both are on the rotor. So therefore we need one rotating rectifier, and which is installed on the rotor itself, and that rotates along with the rotor, and it feeds to the field winding of the synchronous generator. So this is another kind of arrangement. And one more arrangement we can see here is your synchronous generator. It is actually the field of the synchronous generator is fed through the external transformer, and that is being fed by auxiliary supply. So from the auxiliary supply through the external transformer, we are feeding to the field of the synchronous generator through the slip ring. Here we have the rectifier, right? Okay. So now if we'll see another arrangement here, in this arrangement, initially the field of the generator is fed through the auxiliary supply, but after that it is switched to the synchronous generator supply. So when it is switched to the synchronous generator supply, synchronous generator itself, it supplies to its own field, right? So through the external transformer, it feeds to its own field, right? Through the slip ring. Okay, this is another arrangement. And here the similar arrangement here also we have, right? Here we have the AVR unit, and through the external transformer, it is measuring the terminal voltage and feeding it to the AVR, and then it is feeding to the exciter of the synchronous generator through the slip ring. Okay, so there are various arrangements we saw here, because exciter plays very important role in maintaining the voltage, and also it helps to in many cases helps to stabilize the power output or the generator, the power system stability. It helps. We'll see it. So now here another block diagram is shown where we can see a synchronous generator, how it is being controlled, right? We can see here, this is a synchronous generator. This is the here, and we have various measuring elements at different points, and that will be here. Actually, it measures the terminal voltage and current. It feeds through the load compensation to the comparator, right? And the V reference is compared. Then delta V, the error signal, is fed through the amplifier to the exciter. Okay. And also here the exciter output is being measured through the limiters, and it is again fed through the exciter, right? And another block diagram here shown, it is the power system stabilizer. In fact, it plays very important role. You will read this about power system stabilizer, and this needs the signal of in terms of power, omega, that is speed of the generator, and frequency. It is fed to the PSS, and the PSS output is fed through the AVR to the exciter. Okay, so this is how the generator control action is being initiated, right? Okay, so these are the general block diagrams, general discussions. Now we'll see the modeling. We'll start the modeling of the generator. So before moving to different components of the generator, we must first model the generator itself. So as I told, the generator has two components, major components. One is your armature winding, which is on the starter of the generator, synchronous generator, and another is your field winding, which is placed on the rotor itself, right? So we'll see here the figure, the cross-sectional view of a synchronous generator. Okay, and this is how, if we bisect the synchronous generator, we can see the windings and the core section also, the field core and the armature core. So this is your armature core outside we are seeing, and this is your field core. And in the armature core, we have the armature windings. Because we have three-phase distributed winding, so it is arranged in the fashion so that the axis of the field of each phase will apart 120 degrees from each other, right? So now if you'll see the winding arrangement of phase A, now this is shown through A and A dash, right? So this is phase A winding. Now, if we see the axis of the magnetic field axis of the phase A winding, this is here, okay? As the current here is coming up, okay, and here it is going down, okay? So then, therefore, your magnetic axis will be here, okay, in this position. Now, if we'll see the phase B magnetic axis, here is your phase B, right? B and B dash. Okay, B and B dash. So this will give us the magnetic axis here, B axis, right, which is leading A axis by 120 degrees, right? Similarly, for phase winding C, CC dash, your magnetic axis will be here, right? This is your C axis, right? Now we saw the magnetic axis for phase A, phase B, and phase C, right? Now we'll find the axis for the field winding. So what are the field winding we have? We can see here we have many field windings here because I told previously also we have main field winding and also we have damper winding, right? Okay. So therefore, if we consider field winding, that is represented by FD. Okay, you can see here FD and FD dash. They are the field winding. Okay, and of course, the magnetic axis of the field winding FD and FD dash will be here in D axis, right? Okay, and similarly, if we'll consider one damper winding on the D axis, that is 1D and 1D dash, then the magnetic field axis will lie here, D axis. Similarly, in the Q axis, if we'll see the quadrature axis. So in the quadrature axis, if we have two more damper windings, that is 1Q and 2Q. In the D axis, we have FD and 1D, right? And in the Q axis, we have 1Q and 2Q. So therefore, our Q axis will lie here for both 1Q and 2Q. Okay, so this will be 2Q. Okay, so this is your D axis component. This is your Q axis elements. D axis elements, Q axis elements. Okay. Now this is your basic structure. Considering this structure, there may be different structure for various analysis, but we'll consider here. In this analysis, particularly, we'll consider this model. Okay, that is called 2.2 model. Okay. I will tell you why it is called 2.2 model. So now if we'll see the equivalent form of the whatever I have shown in the cross section, the equivalent circuit diagram. Now on the phase A axis, we have one winding right here, and let us say the current flowing out of this winding is IA, and the voltage, terminal voltage in the winding is VA. Similarly, in the B axis, we have the current coming out of the winding is VIB, because when the generator is connected to the load, the current is always coming out of the terminal, right? And the terminal voltage is VB. Similarly, for C axis, we have IC and VC. But if you'll see the field winding, in the field winding, we are feeding the current inside the field winding. So therefore, the current is going in to the field winding here, IFD. And similarly, I1D is also, the current is flowing inside the damper winding. Similarly, I1Q and I2Q. And the terminal voltage, respective terminal voltages are marked with VFD, V1D, V1Q, and VTQ. So now if we'll see from this, by considering different elements, we'll have different models, right? So based on the number of windings in the Q axis and number of windings in the D axis, we can have different models. So IEEE has formulated these models, and for different models, different derivations we'll have. But we are considering here 2.2 model. Okay, why it is 2.2 model? Because we are considering 2 winding in the D axis and 2 winding in the Q axis. Similarly, we can consider also 1 winding in the D axis, 0 winding in the Q axis. That is 1.0 model. And if we consider 2 winding in the D axis and 1 winding in the Q axis, it will be 2.1 model, right? 1 winding, it will be 1.1 model, right? Similarly, 1 winding in the D axis, 2 winding in the Q axis, we'll have 1.2 model, right? And finally, if we'll have 3 winding in the D axis and 3 winding in the Q axis, it is 3.3 model, right? So these models are available in IEEE, and we'll consider here 2.2 model, and also we'll see how to derive the equations for 2.2 model only. Okay, then we'll start writing the basic equations for stator and rotor circuit, and then also we'll write the Fox linkage equations, and from gradually we'll derive the stator algebraic equations, and also then we'll go forward. Okay. So first, considering the stator and rotor of the rotor winding of the voltage equation, this is your equivalent circuit shown as I shown previously also. Here it is shown, right? And now considering this equivalent circuit, we'll now find out the stator equations. So if we consider the stator equation, let us say consider the phase A. Okay. So for phase A equation, if we write the electrical equation at the terminal, so I can write VA equal to minus RSIA, because here the voltage induced is d lambda A by dt. But lambda A is nothing but the flux linkage in the winding A. Okay. So that is d lambda A by dt is the induced EMF. So therefore I can write the terminal voltage equation here. VA will be equal to minus RSIA plus RS is your resistance of the winding. Okay. So minus RSIA plus d lambda A by dt. Okay. Similarly, for phase B, if we write the equation, it will be VB will be equal to minus RSIB plus d lambda B by dt. Okay. Similarly, VC will be minus RSIC plus d lambda C by dt. Okay. So these are the terminal equations of these 3 windings: phase A, phase B, and phase C. Now, if we will go to the rotor equations, rotor voltage equations, so we have 4 windings in the rotor, 2 on the D axis and 2 on the Q axis. So for D axis, if we write the equation, okay, so if I write VFD, so here we are feeding the current to the field. The current is going into the field, and the induced EMF is being induced. So therefore, VFD will be equal to RFD IFD. RFD is the field resistance. IFD is the current flowing in the field winding, right? So VFD will be equal to RFD IFD plus d lambda FD by dt. That is the voltage induced in the field winding, right? Similarly, for the damper winding 1D, I can write V1D will be equal to R1D I1D plus d lambda 1D by dt. Similarly, for V1Q, for 1Q winding, I can write V1Q equal to R1Q into I1Q plus d lambda 1Q by dt. Similarly, for 2Q winding, V2Q equal to R2Q I2Q plus d lambda 2Q by dt, right? So then we found the voltage equations. Now I want to find the flux linkage equations. Lambda A, lambda B, lambda C, lambda FD, lambda 1D, lambda 1Q, and lambda 2Q. So how can you write the equations? Stator and rotor winding flux linkage equations. In the same fashion, we can write the flux linkage equations. So now I'll write the lambda A equation. Lambda A, lambda B, lambda C. Three equations. Now I will write the flux linkage equation in terms of the inductance and the current. Okay. So first I will consider the stator inductances, mutual as well as the self-inductance. And then I will consider the mutual inductance between the stator and rotor circuits, right, individually. So first I am considering flux linkage in the phase winding A, right? So that will be because of the IA, IB, right, and IC. And similarly, that will be because of IFD, I1D, I1Q, and I2Q. So if we'll see, considering the inductances, if I'll write the flux linkage because of phase A itself, I can write LAAIA. It will be obviously minus because the current is coming out of the circuit. Similarly, it will be LABIB, then plus LACIC, right? If I'll just expand one equation, I can show you that will be LAAIA minus LABIB minus LACIC. This is because of the starter currents. Okay. Now, because of the rotor currents, what will be the linkage in the phase A winding? That will be, of course, positive because the current is going in. So I can write LAFD. It is because of the FD current. So LAFD IFD plus LA1D I1D plus LA1Q I1Q plus LA2Q I2Q. Okay, so this is one equation, and it is all three equations are written in the matrix form. Similarly, I can write the equation for lambda B, then lambda C, and I can write all these three equations in the matrix form, right? So that is what it is mentioned in the matrix form. You can see here lambda A, lambda B, and lambda C. All three equations are written in the matrix form, right? Now, if I write in the matrix form, so is lambda ABC will be equal to minus LSS. That is I can write just representing the starter side inductance as LSS into IABC. Okay. Similarly, if I write this matrix as LSR, that means the inductance of the starter with respect to the rotor. Okay. So that is LSR. So minus LSS IABC plus LSR I rotor. Okay. Then I can write the flux linkage equation for the rotor circuit. The flux linkage equation in the rotor circuit, if I write, I can write similar fashion I can write. Okay. First I'll write suppose lambda FD, that is flux linkage in the main field winding of the rotor. So LFD, it is because of the starter, I can write it as minus LFDA IA minus LFD B IB minus LFDC IC. It is because of the starter. Now because of the rotor, I can write LFDFD into IFD plus LFD1D I1D plus LFD1Q. LFD1Q will be 0 because we can see the displacement between D axis and Q axis is 90 degrees. So therefore it will be 0. So therefore no need to consider this. Okay. Similarly, LFD I2Q, okay, LFD2Q will be also 0. That the mutual inductance between Q axis and D axis will be 0 because they are 90 degree apart, right? So therefore this is not considered. Similarly, I can write L1Q. Similarly, for others, between these mutual inductances are considered to be 0, right? Okay. Similarly, writing all flux linkages between starter and rotor. So we are writing the flux linkage in the rotor circuit, then it will, if I'll combine all the flux linkage equation in the rotor circuit, it will look like this in the matrix form, right? So that is lambda FD, lambda 1D, lambda 1Q, lambda 2Q will be equal to this matrix, that is LRS matrix into IABC. It is the vector of the currents, three-phase current. Similarly, plus LRR is the rotor inductance matrix into I rotor. Okay. So now if we'll combine, and in the matrix form, I can write lambda rotor is equal to minus LRS IABC plus LRR I rotor. Okay. So this will be your flux linkage equation in the rotor. Okay. Okay, so this is all about, we have started the modeling of the synchronous generator. Only voltage equation and flux linkage equation we have seen. So today we'll stop here, and again we'll see in the next class. Okay. Thank you very much.